Hi everyone, and welcome to the TLE PCD for Leetcode Weekly 452. Before we start, can someone just drop in the chat if I'm audible, just to confirm? Welcome to the PCD for week 452, Leetcode Weekly 452. Can someone just drop in the chat if I'm audible on the YouTube chat? Okay, so before we start, I would like to tell you that if you're new to TL Eliminators or if you're struggling with your competitive programming journey, then TLE Eliminators offers self-paced courses, uh, which are there for all levels, whether you're a beginner or an intermediate. Like we have four different levels which you can check out on the website. And in our self-paced course, you can get video lectures, curated practice problems. Each practice problem has a dedicated set of hints, as well as dedicated video solution, and then we have a team of doubt support mentors who are available at almost all times. And you just need to create a new doubt, and a mentor will pick it within 10 to 15 minutes. And a high rated mentor will go through your code, will help you solve it and give you suggestions. So, if you're feeling like you're stuck at solving only one or two problems in a contest and you want to improve, I highly suggest, checking out the self-paced course, which is live on TLE's website right now. All right. So now let's get into the contest discussion, the PCD. How was the contest? I felt AB were pretty easy, and then CD were like on the harder side, I think. Um, at least that's what I felt. I've not done lead code that much, but yeah. Um, Partition array into two equal product subsets. So this is the first question, and let's see how to deal with it. Um, we are given an integer array nums containing distinct positive integers and an integer target. We need to determine if we can partition nums into two non-empty disjoint subsets, with each element belonging to exactly one subset, such that the product of elements in each subset is equal to target. Return true if such a partition exists, and false otherwise. So, for example, um, basically what we need to do is we are given some array and we need to partition it in such a way such that the product of, and the partitioning does not need to be a sub or anything. It can just be like some elements. So we choose some elements and their product should be equal to some target. Let's say target was 6, and the remaining elements, their product should also be equal to the same target. So we have to make exactly two subsets. That means the ones which are chosen and the ones which are not chosen. We can think of it that way. And the chosen one's target should be, the product should be equal to the target, and the not chosen one's product should also be equal to target. So basically, this is the idea. So on the face of it, it doesn't look that easy. But then when you look at the constraints, it says that nums.length, that is the number of elements, is less than or equal to 12. So n is, let's call n as the length. So n is less than or equal to 12. That is the first thing. And our target is less than or equal to 10 power 5. Okay. So in this question, the constraints matter a lot. And as you observe, since n is less than or equal to 12, what we can do is we can brute force over all 2 to the power 12 subsets. We can brute force over all 2 to the power 12 subsets, and so simply take O of 2 to the power 12, right? And then for each subset, we can find which belong into the subset and which do not belong into the subset, and that will be like times n into the complexity. And then in big O of 2 to the power 12 times n, we can find out our answer. So basically the idea is that given like, so let's say we were given four elements, right? So one way is that all four are in the same subset. Okay, so we can represent that as all as zeros. Then we can say the first one is in a different subset, and the remaining, or we can say first from either side. So we can say first one is in a different subset, and remaining are in a different subset. And then we can have the second one is a different subset, and this one is a different subset. And then we can have the last two are in a different subset. Stuff like that, right? And this can go on until we get all ones. So all of them are in the second subset. Now observe that it says our subset should be non-empty. So since it should be non-empty, we have to ignore this case and we have to ignore this case. But all the other cases are valid, right? So now how do we check all the cases? Like how do we write a brute force for this problem? And the idea is it can be done in two ways. Actually, it can be done in many ways, but the two main ways is either use bit masks. Okay, so if you're familiar with bit masks, either use bit masks or you can use recursion. And I think in recursion, the stack limit should not exceed. I'm not 100% sure because I did not do recursion. But yeah, I think both ways are possible. I will go with the bitmasks approach since it's more clean. And the idea of bitmasks is if you observe the set and like which elements are in the set which I've chosen, which elements are not in the set I've chosen, then it basically just forms binary numbers starting at 0. So these are all binary representations of 0 all the way to 2 to the power n minus 1. So what I can do is I can take a variable called mask. So if you're familiar with bitmask, this should be very easy to understand. If this is the first time seeing bitmask, then it might not be that easy to understand, and you can read about bitmask. You can also solve it with recursion. There is no problem. So we can try all the values of mask from 1, 2, 3 all the way to 2 to the power n minus 2. Why minus 2? Because we don't want this case and we don't want this case. And we try all the possible values of bitmask. And according to which elements are taken in our bitmask, those elements we put in the first set. So we take product of the elements where the binary value is 1, and we take product of the elements in which the binary value is 0 in the second set. And then we check if this product is equal to target here, and we can check if product is equal to target for all the ones which are 0. Why use bitmasks when we can just square and typecast the target variable? What do you mean square and typecast? I'm not sure what you're talking about. First of all, if you have the target variable, which is 10 to the power 15, if you have 10 to the power 15, if you want to take square of 10 to the power 15, that will be roughly 10 to the power 30, right? And this will overflow long also. So you need to use int 128, and I'd rather not use int 128 while solving. So, and I don't know, unsigned long. Will it fit in unsigned long? I am not 100% sure. Uh, I'm pretty sure it won't fit in unsigned long as well, will it? Okay, yeah, it might actually fit in unsigned long. Okay, that is a nice solution. But I'm telling the approach which I found straightforward on looking at the question. So, okay, nice approach, Ishan. Yes, nice approach. Because yeah, it will just fit in unsigned long. 10 power 30 will just fit in unsigned long. But yeah, all right. I think the bitmasks idea is more applicable to other problems as well. So in a sense, it's a more general idea. But yeah. So let us have a look at the code briefly for this. So what do? We start our mask at 1 and we go to 2 to the power n minus 2. So we have like a mask from for mask. So let's call that MSK, and we go from 1 to 2 to the power n minus 2. So these are all the possible values of our bit mask. And then we have a product of 0, the places where the bit mask was 0, and product of places where the bit mask was 1. So basically first set and second set. If that bit is on in our bit mask, so that's what I said. If that bit is on in our bit mask, then it goes into product 1, like we multiply product 1. Otherwise, we multiply product 0 with that value. So for like we have product 1, which is product of uh product of places where the bit mask is 1, bit mask 1, and product 0 is places where bit mask is 0. Product of all the values at indices such that the bit mask is 0. All right? At those bits, like those specific bits where the bit mask is 0. And if at any point the products become bigger than target, then we can break because we know the product has become too large already. And this is the important step because if you're storing in ordinary long, if you observe the constraints, if since nums goes to 100, um, yeah, since nums goes to 100, it might overflow long. So that's why if ever the product becomes larger than target, I break. And at the very end, if for this bit mask, the product 0 is equals to target, product 1 equals to target, I can return true. And at the very end, if I've tried all bit masks, if I've tried all bit masks, if I've tried all bit masks and none of them worked, then I know that it's not possible and I return false. And that's the bit mask solution for this problem. All right. So if product 1 equal to product 2, sorry, product 0 equal to our target. So if the first set's product is equal to second set's product is equal to our target, we can return true, return true. Otherwise, outside this loop, once we have checked all the possible masks, all the possible subsets, we can return false. And if you're not familiar with this method, you can Google or you can look at TLE's course also. I think we have this in like level 2 or somewhere where um, you can search for how to find all subsets, how to brute force all subsets of an array using bitmask, or just how to brute force all subsets of an array. So yeah, this is the idea, and you can do it with recursion as well. So yeah, moving on to the next question, B. Oh yeah, we'll just talk about the time complexity. So as I discussed, there are 2 to the power n possible bit masks because we're running from 1 to 2 to the power n minus 2. And then to check each bit mask, it's another n. So the final complexity is big O of 2 to the power n times n. Okay, problem B. So problem B is again a very brute force-ish type of question. Uh, Not very interesting question according to me, but okay. You are given an m into n integer matrix and an integer k. For every k into k submatrix of grid, compute the minimum absolute difference between any two distinct values of the submatrix. Minimum absolute difference. That means basically like Euclidean distance or something like that, like minimum absolute difference between any two distinct values of that submatrix. And note that distinct values. Okay, so like if two values were like 3, 3 in that submatrix, the answer will not be 0 because 3 and 3 are same, so we need to take only distinct values. Fine. Return 2D array answer of this size, obviously if you take k into k submatrix, then the size of the answer will be m minus k plus 1 times n minus k plus 1, where answer of ij is the minimum absolute difference in the submatrix whose top left corner is ij in grid. If all elements of submatrix have the same value, answer will be 0. Okay, so let us try to understand the problem first. So if we are given a matrix, let's say 3 by 3 matrix, and our 3 by 3 matrix is something like 2, 3, 4, 3, or 4, 5, 6 maybe. And then we're given another 6, and then we're given 7. And here, let's say we're given 7, 7, 7, 7. And then let's say 8, 10, something like this. And our k equals 2. Fine. So basically what it's saying is, for this submatrix, so this is our 3 into 4 matrix. Right here, m is 3, n is 4, and k equals 2. So this is our 3 into 4 submatrix. Now, if k is 2, then we need to check all 2 into 2 submatrix of, sorry, this is our matrix. So we need to check all 2 into 2 submatrix of our matrix, and then we need to find our answer. So in this, what are the distinct values? Here, all the values are distinct. So we have 2, 3, 4, 6. Now, if you find difference, so to find minimum difference, one way is to compare all pairs. But if we have the elements written in sorted order, then we can just compare adjacent elements. And we can say difference between these two is 1, difference between these two is 1, and difference between these two is 2. So here minimum is 1. So minimum for this submatrix will be 1. So our answer looks something like this, 1 over here. Now let's check the next submatrix. So erase all this and we can go to the next submatrix. And let's say our next submatrix is something like this, right? So here what's the minimum difference which happens? We have 3, 6, 7, 8 if we write them in sorted order. Here the difference is 3, here the difference is 1, here again the difference is 1. So the answer for this submatrix will be 1. And let's move on to the next submatrix. So I think you got the idea. So let's just consider some special submatrices. Here the value is all 7s. So there is only one value 7. And what should be our answer in this case? The question says, if all elements in the submatrix have the same value, the answer will be 0. So for this particular answer, the value is going to be 0 here. Okay. What about a case where we have like 6, 6? So consider this submatrix. Here, since 6 and 6 are duplicate, right? So we cannot write 6, 6 in our, like, array without duplicates. So we need to remove duplicates from our array, and then we need to find answer. So this will be 2 and 1. So here the answer will be 1. And here the answer is going to be 1. You can check. And here the answer is also going to be 1. So something like this will be our answer. And you can observe that this is the height of this is m minus k plus 1. Height of this will be n minus k plus 1, because that is how many submatrices are being found. Okay, so how to approach this problem? First, let us see the constraints again. So let us see what the expected time complexity will be. Again, we can see that the constraints are very small in this question. So we have n comma m. So height and width is less than equal to 30 for our matrix. And then each value goes up to negative 10 to the 5 to 10 to the 5. So that part is fine. And k is obviously less than equal to minimum of m and n. That's also fine. So this is our um, key idea that n and m is very small, right? So basically what we can do is we can write this kind of algorithm because the n and m is very small. And once we think of this algorithm, you can see that it matches the time complexity. And the algorithm is for every submatrix, for every submatrix. So for every submatrix means we'll iterate over all possible starting I and j of that submatrix. So for every submatrix, and this to find this will take big O of nm to go through every submatrix. This step will be big O of nm. We will find all the elements, find all elements of that submatrix. So for example, the same way we found that this submatrix has elements 2, 3, 4, 6, we can write this in 4 loops. Like we can write it in 2 loops, like start from here, go up to k in both direction and find all the elements. So find all the elements of the submatrix, sort them, remove duplicates, remove duplicates. So find all elements will be how much? It will be big O of k square. So since k can go up to n and m, so basically this is also like big O of nm only. So roughly big O of nm itself. Sort them will be big O of nm log nm. Okay. Remove duplicates will be again big O of nm. And then once we have sorted, so like I mentioned before, if we want to find minimum difference between any two values, if once we have sorted, we can simply check difference from I plus 1 to I for all I in that array. So find minimum difference. Basically, we need to find difference array and we need to find the minimum difference. Find min difference, and this is also big O of nm itself. So what is the total time complexity of this? Well, um, in the outer loop, the time complexity is big O of nm, and in the inner loop, the biggest time complexity we have is nm log nm for the sorting. So we multiply these two time complexities. If you can observe, this term dominates over these other terms. This term dominates over these other terms. So the final time complexity we get is big O of n squared m squared log nm. Now this is somewhat on the boundary for the given constraint. Yeah, we can use set. Arpit, we can use set, or we can sort. There is no problem. Yeah. Let us just check if this is enough for the constraints. So we'll go to Desmos and we'll just plug in the values. So we know n equals 30, that is the max value, m equals 30, and n square m square log nm. And we can see that this is roughly 2.3 times 10 to the power 6. So roughly 2.3 times 10 to the power 6 operations, which is fine, like which is a bit near the limit, but yeah, we can do up to 10 power 7 operations, so it's fine, it'll pass. And yeah, we can use set instead of sorting it manually, like instead of storing in a vector and sorting, we can obviously use set. So then this step will become log nm, and we don't need this step, and we don't need this step. So yeah, that's also a possibility. So that's all. It's a very basic brute force question again. Like I think the first question was brute force is also brute force. We go through every submatrix, find all elements, sort them, remove duplicates, find the minimum difference. And the key idea is uh, on sorting, the minimum difference will simply be ai plus 1 or vi plus 1 minus ai, and minimum of that for all the possible I values. So minimum of this, because once we have sorted, we have all the points, like all the points, let's say 1, 4, 7, 9, and they're like on a line now. So we don't need to compare difference between these two because we're trying to find minimum difference. We just need to compare difference here, which is 3, and here, which is 3 again, and here, which is 2. And we can see that minimum difference is 2 directly. So that's why we're solving it like this. Um, let's have a look at the code for this. We already discussed the time complexity. So M and N is our, you know, height and width. So we're just defining that. This is our answer vector, and we are going from I equals I less than m minus k plus 1, n minus k plus 1. Here is the vector which we'll push back into answer. So we'll just push into this vector and then we'll push it into answer later after we're done. Now we're iterating over all values of j. And here is the vector submatrix. So in this vector submatrix, we'll store all the values of the submatrix over there. So we can loop through, let's say ix is equal to I, then ix goes to I plus k. Similarly, jx equals j, jx goes to j plus k. And all these values which are there in my current submatrix, I add here. I sort the submatrix, and then I make sure that any duplicate values are removed. So one way to do it is like this. Other way to do it is just use a set or something like that. Yeah. Now, if the submatrix size is equal to 1, that means all the elements were equal to one element itself. So it is like this case over here with all sevens. So some case like this happened. In that case, the answer is 0 because that's what they said in the question. So we do that and we continue. Otherwise, we find the minimum difference. We set it to int max. Minimum difference equals, here it's L. So submatrix of L minus submatrix of L minus 1. We push back that minimum difference. We push back this vector in answer and then we return the answer. So basically another brute force question with a direct answer. Is that clear? Yeah. Second question is definitely, I don't know, maybe second question is easier. A is also very easy because if you know the subset idea, it is very easy. Yes, third and fourth question we're just going to go to it. Fourth question was pretty hard this time. I could not solve within the contest. I had to upsolve it afterwards. Or at least I felt so. I don't know. Okay, we're moving on to problem C. If anyone has any doubts with B, write it in the chat right now. Otherwise, we'll move on to the next problem. Yes, third version is about bitmask, but not exactly DP, just bitmask and BFS. Yeah, you can do BFS. Yeah, I also did BFS only for it. Bitmask BFS. Okay, let's have a look at the third question. You are given an M into N grid called classroom, where a student volunteer is tasked with cleaning up litter scattered around the room. Okay. Each cell in the grid is one of the following. S is the starting position of student. L means it's a litter which must be collected. Once it is collected, the cell becomes empty. R is a reset area that restores the student's energy to full capacity, regardless of their current energy level, and it can be used multiple times. So basically, it's like a place where you can reset your energy and you can continue. You're also given an integer energy representing the student's maximum energy capacity. And the student starts with this energy from the starting position. So basically, from the starting position, you have full energy. You go and you collect litter, and then when your energy gets less, you go to some square where there is R, and you can reset your energy and go back. Okay. Each move to an adjacent cell, adjacent is up, down, left, right, costs 1 unit of energy. If the energy reaches 0, the student can only continue if they're at a reset area R, which resets the energy to maximum capacity. Return the minimum number of moves required to collect all litter items, or -1 if it's impossible. So first off, let us um, let us understand what the question is asking. So we have a grid again, a lot of grids this time. We have a grid, and the size of this is called the classroom. The grid is called the classroom, and the grid is m into n size. And each cell of the grid has some value. Okay, so I'm just drawing some random grid here. It has some value, and this is given as input to us. So let's say the grid has some value like this. And then if there's a dot, that means it's an empty space. If there's an S, this means this is our starting position. And then this is blocked. So I think that's what they said, right? Uh, X means blocked. Okay. So X means it's a blocked cell. So we can't go here. So let's say these were blocked. And L is a litter. So L is like trash which we need to collect. So let's say there are some cells where L is there. Okay. And there are some blocked cells. And there are some points where we can reset our energy. So let's say these 2 points we can reset our energy. So basically our idea is we have some initial energy value E. We are starting from this starting position and we can go anywhere. One step costs us one value of energy. And so for example, one way is like we collect the litter here, we get new energy, we collect litter here, go down, get more energy, collect litter, and maybe then if we have enough energy left, we can collect litter like this. Okay, so first of all, it's like a traversal type of problem. So we should have, some intuition that maybe some BFS or something like that will come into play. And the first way to like approach the problem is again look at the constraints. So here again in all the questions, the constraints are becoming very important in this contest, ABC. And the reason is here again the constraints are very less. So you should get an idea that we should somehow brute force or do something like that of the states. So we know that n and m is less than equal to 20. It's given in the constraints. And we also know that the energy is less than equal to 50. So our starting energy and our reset energy is less than equal to 50. And we also know that there are at most 10 L cells in the grid. So at most 10 pieces of litter. Okay. So let us think about how to take advantage of these small constraints. Because whenever you see small constraints in a problem, that should tell you it's going to be some way like you must somehow take advantage of this constraint. So let us see how many possible states there are for collecting our litter. So at any moment of time, obviously our x coordinate and y coordinate, that will be part of our state. So let's write state here. And this is important because we're discussing how many states like there can be there, how many possible conditions can be there for our state. Okay. Then there can be the pieces of litter we have already collected. So like this is a subset of litter which we have already collected. Subset already collected. So this is going to be our subset which we have already collected. And we are at some position X and Y. And the last thing we have is our energy value currently. And if you observe, this state defines everything about our current position. Like we are at position X comma Y. We have collected this piece of litter and our current energy value is E. So if we can somehow brute force all the values of this state, if we can brute force all the values of this state, and we can check which one is the most easy to reach, like which one takes the minimum steps to reach, then we got an answer. Also, if we cannot reach a state where all the values are corrected, where all values are collected, so yeah, we need to reach final states, and final states are ones where all values of litter are collected. All values of litter are collected. So if we can't reach a state like that, then our answer is -1. Otherwise, we need to find a state which we can reach such that all values of litter are collected and the number of steps to reach that state are minimum. Okay, so first let us see how many states there can be. So since x and y can go up to n and m, so the number of states will be 20 times 20. Now here again we have a subset of the litter which has already been collected. So at most we have 10 pieces of litter. So if we have some scheme to number a litter, like we number this litter as litter number 1, litter number 2, litter number 3, and litter number 4. So we can say that, okay, I collected litter 2 and 3 till now. I need to still collect litter 4 and 1. So this part can be represented using a bit mask again. A bit mask of 2 to the n or 2 to the L. Let L be number of litter. So this can be represented using a bit mask of 2 to the power L. So at most it will be 2 to the power 10. Since there is 10 litter, each litter is collected or not collected. So if it's not collected, we can say it's 0. That position in our bit mask will be 0. If that litter is collected, then that position in our bit mask will be 1. So this means if we have a bit mask like this, it means that litter number 1 is not collected, litter number 2 is not collected, litter number 3 is collected, and litter number 4 is not collected. So that's what our state will mean with this bit mask. So then this becomes 2 to the power 10. Okay. And what is the possible value of energy? Well, it will be from E equals 50, energy is at least 50 to 0. And if your energy is 0 and you're not at a reset state, then we don't even need to count that state since it's like a dead state. So basically 50 states itself. And so this is the number of states. Now our question will obviously be, can we do brute force? Are these states less enough that we can do brute force and check all the possible states? Can we do brute force? Okay. Can we do brute force? So again, we can set some values of n and m and check this. So that's 20 times 20 times 2 to the power 10 times 50. And if you observe how many states are there, it's roughly 2 times 10 power 7 states, which are possible. And will this be brute forceable? Again, the answer is yes. Yes, it is brute forceable, but it's just on the border. So if we have very high constant factors in our code, it might TLE. So we know that roughly, around 10 power 7 or 10 power 7 to 10 power 8 basic operations we can do. So these many states we can definitely check, but we need to be very efficient about how we're checking all the states. And actually not that efficient also. Like I didn't write that efficient code as well, but still it got accepted. So yeah, like some amount of efficiency. We can't do too much recursion and stuff. Otherwise, recursion gives a lot of overhead, so it might fail if we're not careful. But yeah, basically the idea is, since the number of states is this much only, we can brute force through all the states and find the answer. Is that much clear? Now the question is how to brute force. The question is how to brute force. All right. So um, our idea is going to be that each state, so for example, if we're at a current state, right, and we go to an adjacent value, so we can either go like our x coordinate becomes +1, or our x coordinate becomes -1, y coordinate also becomes plus or minus 1. And then if we have an R, so we need to keep into mind all the conditions of the question. So if we have an R, then the energy becomes reset. And if we have a piece of litter over here, so we can add a new litter into our bit mask. Like we have collected this litter also since we reached this square. So once we keep track of all of that, we need to start at our starting state. So our starting state is something like this. It will be, so let's say xs, ys. So this is my coordinates of my s in my grid. So this will be my starting state. And in the start, we have collected nothing. So our bit mask will be all zeros because we have collected nothing. And then the energy we will have is the full energy because in the start, we start with the full energy. So this is where we start. And then the distance to this starting state is of course zero, like number of steps to reach starting state will be zero. And what we do is we can do a BFS. Why do we do BFS? Since we want to find states with minimum distance first. So what we do is we do a BFS over the space of states, some kind of 4D BFS almost. So 4D BFS over the possible states which we can have. So let me just clarify what I mean. So basically from this starting state, we can check all four directions, up, down, left, right. So these are the possible four directions, right? So we check, okay, if we go right, then our energy will become -1. Okay, our energy will become -1. And if there is a litter, then we will mark that that litter has been taken. If there was no litter, then the bit mask will be the same. So bit mask will be OR zeros. If that cell was L or not L, okay, the energy has become -1. And our Y coordinate, because we moved right, our Y coordinate has increased by 1. So this becomes our new state, basically. And if there was R, then energy becomes E again. Energy becomes full energy. It does not become E -1, it becomes E. So we need to keep basically these things in mind. And we need to, and yeah, distance to this state will be simply distance to my parent state. So here my parent state was the starting state plus 1. This is the number of steps to reach this state. And because we're doing in BFS order, that means we're using a queue where the minimum distance state will be first. We will visit each state with lesser distance before a state of higher distance. So basic, and also we need to maintain a visited array to ensure that we don't revisit states. Ensure not to revisit. Ensure not to revisit. And second thing, BFS order of states. So we're basically doing a brute force itself, but we're doing in a BFS order. So that way, increasing distance from the start state. So that way we're visiting the, minimum distance from the start state first. So we're basically visiting the states in an order of how close they are from the start state. Increasing distance of state. So how does this help us? Because the first time we find a state where the bit mask is all ones, we know that that is the answer and we can simply return the distance taken to reach there. So let me just make this concrete by showing the code because till now I think it's very theoretical. So if you're familiar with the ideas, you'll find it very easy. Otherwise, you might be finding it pretty hard. So the idea is we have an m into n grid. So okay, we marked that. Now for each value, so first we store the starting position. So simply if the classroom ij is s, so that's our starting position. For each litter, okay, we push back into this vector. So we're marking all the litters and we're also marking litter ID. So the first litter we see, we give an ID of 0. The second litter we see, we give an ID of 1 and so on. So basically the same way I did in this graph, except instead of 1, we'll mark this one as 0 and then we'll mark this one as 1 and 2, and this will be litter 3. So basically that's what we're doing. Yeah, that's what we're doing here. So something like that. Yeah. So why are we marking litter? Because we need to know which element of our bit mask to modify when we take that particular litter. So that's why I have a map from the coordinate of the litter to the ID of the litter. And L becomes then the count of litter as well. So I'm keeping track of where the litter is, what ID that litter has, and where is the start element. Okay. Then I'm creating an array called visited, which is a Boolean type array. It's either true or false. Its size is 20 into 20 into 2 to the power 10 into 51. So basically what this means is I visited the following state. Have I visited the following state? The state will simply be um, so all the possible states basically will have true or false. Have I visited before? And the only reason I'm keeping this is so that we don't revisit states again. Now we're going to define a structure called state, which will go into our BFS queue. The state will have the positions X, Y, the bit mask, so how much litter we have collected, which litter we have collected. E is the current energy at the state. D is the distance from the starting state. So D is the distance from the starting state. The same way we would have in a BFS. We make a queue for the BFS where we put our structure state here. We mark the first state as visited. So I mentioned that the first state will be simply the starting coordinates X and Y, 0 for the bit mask because none of the litter has been connected, and the energy. So we mark that state as true, and we also push that state into our queue. This is just a helper vector for all the possible directions which we can go from a given state. Okay. So now for each state, what do we do? While the queue is not empty, so while the BFS is still going on, so this is basic BFS code. Um, we take the top from the queue. So the closest state we pick out from the queue. If that queue's bitmask is all ones, so if it is 2 to the power L minus 1, so like I mentioned, if it is 2 to the power L minus 1, then we can simply return the distance required here. So return the distance. And why are we doing this? Because once it is all ones, that means we collected all litter. So once it is all ones, we have collected all the litter and we can simply return distance. So this current state u dot d. D is the value storing the distance for our state. Otherwise, if the energy at my state is zero, if the energy at my state is zero, I can't go anywhere else because now the energy is zero. I have no energy to move anywhere. So the state basically dies off and we can just continue. If I still have energy to go other places, then we can get into this loop. And for every adjacent element, so we're taking each direction we can go. So for every adjacent element, I find my nx and ny, which is my new value of x, new value of y, if I go in this particular direction. And we first check if this value is valid. So if nx is less than 0, obviously it means we went outside of the boundary. So here I'm just finding for a given node, what are the adjacent nodes. So for this node, here this will go outside of the boundary. These two are adjacent nodes, and this one is a blocked node. So I can't go here, I can't go here, but I can go to these two states. So that's what I'm doing. If it's a blocked one also, I continue, or if it goes outside the boundary, I continue because this is not a valid adjacent element. So it's a very similar to like grid BFS or flood fill BFS if you're familiar with it. Um, so yeah, the new value of energy will simply be the old value of energy minus 1. Why is that? Because to go to the next step, our energy decreases by 1 for this new state. But if the value of classroom at nx ny was r, that means it is a reset, right? So in that case, the energy becomes the full energy. So our energy has become reset to full energy, and we can write new energy is the full energy. Then we need the bit mask. What is the bit mask of our next state? Well, it will be the same as the bit mask of our old state. But if this current position, new position, if it was a litter, that means this litter got collected. So we can include that litter into our bit mask. So we can do new mask is the old mask, and we OR that with one left shifted by the litter ID. So basically, if we were at some point in our grid, if we were, let's say, at this point in our grid, and we're trying to go right, and that's a valid state, and there's a litter over here, okay? And here, let's say my bit mask was 1101, or maybe 1100, and I have collected, that means the first litter, the second litter, but I have not collected the third and fourth litter. And let's say this is litter number 3. So what happens is I shift my um I shift to the third bit. So actually this should be the left to right, not right to left, but okay. I shift to the third bit and I do OR. So basically I'm saying that the first, second, third litter have been collected and now only the fourth litter is collected. If this cell had a litter and this litter had some litter number, of course. So I can say that this litter number has now been collected and now that's why the bit mask has become 1 at that position. So I do OR equal to with the bit mask. If this current state, nx, ny, nmask any, so now our full state is defined. If it has not been visited, then we mark it as visited and we can push it into our queue. And when we push it into our queue, distance of the state will simply become the old distance plus 1. So we do a BFS, we brute force all the states, but the way we visit the states due to BFS is in order of increasing distance from the start state. If any of the states, if any of the states get a full bit mask, like they've collected all the litter at the state, we can simply return distance to that state. Otherwise, once the whole brute force is finished, we can return -1, saying that it was not possible in any of the states. What is the time complexity of this? The time complexity will be simply, so BFS does not add any time complexity. BFS's time complexity is simply big O of n times m, n plus m, where n is vertices, m is edges. Right? I think you should know BFS time complexity. And here, n is simply number of states. So that's the number of nodes which we are visiting in a BFS. So number of states. M will be at most 4 times n, since each node has at most 4 edges, up, down, left, right. So basically, the time complexity will simply be O of n, which is O of number of states. How many states we had? Again, as I said, the number of states we had was this much, which is roughly how much? 2 times 10 to the power 7, which will fit in our number of operations. Is that understandable? Not able to implement in contest. Yeah, the implementation for this is pretty heavy. It took me also, actually, it took me a big chunk of the contest to implement C, and I could not solve D during the contest because of that. But yes, it gets like with practice, you'll be able to implement stuff faster. So definitely do absolve this after the contest because it'll be very helpful for your bitmask and your brute force ability. Don't look at the code. Try to write the code on your own now that you have the idea about it. And of course, if you want more practice, you can try out this TLE self-paced course. And the problem sets. We have a dedicated bit masking section, I think in TLE level 3 or 4. And you can check out the problem sets and stuff. Okay, let's move on to the last question. Question D. If there are any doubts, please put it in the chat. Otherwise, I'll move on to the next question. Question D was pretty tough question, I think. Um, I mean, like if you make the correct observations, it's not tough at all. But yeah, it also requires you to have good templates or to know, segment trees and be able to Google a segment tree fast enough. Like go to Geeks for Geeks and take a segment tree, or already have a template for segment tree because D, I think, needs a segment tree or some kind of data structure to solve it. Okay, the previous question was clear. Thank you. So we'll go to D now. Let us read the question. You are given an integer array nums having a length n. Okay, a 2D integer array queries where each query is some index, comma value. For each query, we update that index to this value, and then we have to choose some integer k to split the array into one prefix and suffix. So based on k, we split it onto prefix and suffix. such that the sum of counts of distinct prime values in each part is maximum. So what does this mean? The sum of the counts of distinct prime values in each part is maximum. So first let us just take any array and try it, okay? So let's say we have 2, 1, let's just take that example, 2, 1, 3, 1, 2. Okay, so basically we can split array at any point, and we need to count distinct primes here, and we must choose a case such that this sum is maximum. And also, what answer we need to print? Return array containing result for each query in the order they are given. So we don't need to give the value of k, which is the position where it is maximum. We just need to give the value where the answer is becoming maximum, right? Yeah. For example, if you see the outputs, um, they're not giving the position actually. So the question statement is not that clear, but we don't need the position where it's becoming maximum. We need the maximum value itself. So first, without doing any queries, let us find what is the maximum position. So till here, distinct distinct on the left will be 1, and if we take this, distinct on the right is 1, 2, 3. So here the answer will be 4. Okay. And then here the answer is going to be 2 plus 3. So clearly this is 5, which looks to be the maximum right now. Here again the distinct is 3 and here distinct is 2. So answer will be 5. And then here distinct is 3 and here distinct is 1. So answer is 4 here. So in this array, without doing any operations, the max value of distinct primes in prefix plus distinct primes in suffix for any point is 5. And that is achieved at 2 points. 1 point is here and 1 point is here. Okay. The first query. Also, one more important thing. Note that the changes made to array in one query persist into next query. So basically, once we make a change in array, it's not only for this query and we answer it and we live our life. We have to do it for all the future queries as well. So that is one thing to keep in mind, that the updates are persistent. So let us see this example. For the first query, we have to update index 1 to 2. So we take index, is it 0 based or 1 based? Let us just check. Uh, okay, it's 1 based indexing. Yeah. So we update this to 2. So our new array basically becomes 2, 2, 3, 1, 2. And what is the best way of splitting here? Well, if you split like this, which last time was giving us 5, now it's going to give us 1 plus 3, which is 4. And if you observe, uh, wait, one second. Right, okay. Very, very sorry. Um, 1 of course is not a prime number. I do not know why I was counting 1 as a prime number. But yeah, so the previous query, the answer will be 4. And here the answer should be 3 because there is 1 prime here, which is 2. And the other 2 primes are 3 and 2. So the answer will be 2 here. So 1 plus 2 will be 3. And that's the best split we can find in this modified array. So in the original one also, the best split would be something like this. And yeah, the answer would be 3 here as well, since 1 does not count as a prime. So sorry about that. Okay. Um, what about the second query? In the second query, we have 2, 2, 3, 3, 2. So that's what it's been updated to because they updated position 4 to 3. So the array becomes something like this: 2, 2, 3, 3, 2, because position 4 was updated to a value of 3. And now the best split we can get will be something like this. So here we have two distinct primes, which is 2 and 3. And here again we have two distinct primes, which is 2 and 3. So our final answer for this query will be 4. Okay. And note that updates are persistent. So because this was made 2 here, it will remain 2 here as well. So how do we try to approach this problem? Well, the first is first let's look at the time complexity again in case it's like brute forceable or something again, like the previous questions. But no, if you observe n goes up to roughly 5 times 10 power 4, which is almost 10 power 5 itself. Queries also is the same. So we can expect some solution which is big O of n or big O of n log n, something like that. Big O of n root n, max to max n root n, something like this. We're expecting our solution. So it's a more standard type of problem, not a brute force problem. And we expect our solution to be one of these types, something like this. So what observation should we make? Well, one of the helpful observations we can make here, let's call this observation 1, is that if we want to find number of distinct primes, right? So for a given prime, how much does it contribute to some split k? So for some split k, how much contribution happens? What do I mean by this? What I mean by this is, let's say, um, there is a prime number 3. Okay. So the prime number 3 appears in some position here, 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 and there are some elements in between. Okay. So there are some elements in between which don't matter for now. So let's say the prime number 3 appears in these elements, in these positions. Now, the only important ones which are helping for our distinct value answer is the first one and the last one. So the first occurrence of the prime, and the last occurrence of the prime. Because all the ones which occur in the middle, right? All the ones which occur in the middle, either they already have 3 occurring or they'll have 3 occurring later. Like if this was our prefix and this was our suffix, then the first occurrence of 3 is the like one which we care about, because the remaining 3 will be non-distinct. Similarly, last occurrence of 3 is the one which we care about, because the remaining 3 are non-distinct, like they're duplicates. So we only care about the first and last occurrence of some given prime. Okay. And what happens to our answer, which is like the number of distinct primes? So for any prefix which is less than the first occurrence, so let's call the first occurrence of 3 as L. Okay. So for any I which is less than L, the 3 does not contribute to anything. The 3 does not, at least it does not contribute to the prefix. So for any prefix I which is less than L, the 3 is not contributing, like it's not even present in the prefix. So it does not contribute to the final answer for that prefix. Like the count of distinct primes in the prefix is not affected by 3. Now, if we consider some prefix which goes up to here. So let's say this was our k, and we considered this prefix. Now, because I is greater than L, basically this k point is greater than L, it has the first occurrence of 3 in it. And because it has first occurrence of 3 in it, we can add a plus 1. That means that the prime 3 has contributed a plus 1 to our number of distinct primes in this prefix. So basically, if the prime P first occurrence, if for a prime P first occurrence is L, the value for prefix, so we'll store like all the values for every prefix, like the distinct count for every prefix. So the value for prefix for I, where I is less than L, that does not remain changed, or that is added with 0, let's say. And for every prefix such that I is greater than or equal to L, so now in the prefix we have the value of the first occurrence of 3, right? So we increase by 1. And this is for every prime that is present in our array. Okay. So then we found, using this method, if we do it for every prime P in our array, then what happened is basically we can find the number of distinct elements in every prefix for our initial array. Okay. So prefix of I is basically, if we have a prefix, if we have prefix till I, so let's define this as basically an array basically. So if we have prefix till position I, then what is the count of distinct primes? And we can write it like this. So we can, for each prime, each unique prime in the array, we find its first occurrence. And if its first occurrence was less than I, then we can add a 0. Otherwise, we'll add a +1. Okay. Similarly, for suffix, for suffix, for suffix of I, we just need to check if, let's call this last occurrence value as R. Okay. So for a given prime, the last occurrence value of that prime is R. So for a suffix of I, every position I which is greater than R, if the I is greater than R, then the prefix is added with 0. Otherwise, if I is less than or equal to R, then the suffix will be added with a value of 1. Why? Because every point here in this like every suffix which is like this or like this or like this, in that the last occurrence of 3 is there. So 3 is one distinct prime, so we can add 1 to it. But if the suffix was something like this, it would not cover 3. So the prime 3 would not contribute to the answer. So the same way we can calculate the values of prefix of I as well as suffix of I. Okay. So this is our first observation itself. So till now, all this which we discussed can be considered a first observation, that the first and last occurrence itself are determining our answer. Okay. How to calculate and now the second observation is our answer, like if we decide to split the value at I, okay, or if we decide to split the value of k, then our answer is simply prefix at I plus suffix at I, right? So the prefix at I, or maybe prefix at I minus 1 plus suffix at I. So this is our answer if we decide to split the array at the position I. So basically for the initial case, we can find prefix for all primes. We can do the +0 +1 thing. And similarly, we can find a suffix, do the +0 +1 thing. Using the prefix sum, suffix sum idea, we can find the prefix sum of this, suffix sum of this, and we can get answer over here, right? So the initial case without any queries being done, we have solved that part by simply noticing that first occurrence and last occurrence of the prime matters. We can set prefix of I like this, and we can use prefix sums and suffix sums to find the answer at position I. Is that much clear? Can someone tell me if that much is clear? I'll just show you some code for this so that that part becomes clear. So yeah, so the part which I explained so far, this part, the highlighted part, is the code for that. And basically what I'm doing is n is my size of numbers. Um, let occurrences be for now. For now, let's not discuss occurrences. So this is the part which will come up later. But occurrences is basically for every prime, which positions it occurs. Okay. So for every prime, which positions it occurs. So it's a map from prime to a set of positions where it occurs. Okay. Count L and count R. These are uh, count L and count R are basically the prefix and suffix which I talked about. So this one is being called count L and this one is being called count R. Fine. All right. So yeah, or actually count L and count R are the like basis for like we're going to do prefix sums to find the values of count L and the values of prefix L and prefix R, right? So count L is basically the array without doing prefix sum. So anyway, for every number we check if it's a prime. So every number in our array from I0 to IN, we check if it's a prime. How to check if it's a prime? Well, that is very simple. We just do the normal prime check. If it is 1, then we return false. Otherwise, we can check all numbers up to square root of x. And if any number divides up to square root of x, then we can return false. If there is any factor, it will be less than or equal to square root of x, right? So if there is a factor, we return false because then it's a composite number. Otherwise, we return true because we know it's a prime number. Okay, so for every prime, we find the occurrence of that prime. All right. So we find the occurrences of that prime and we insert it into the occurrences. Then for each occurrence, we find the first and last element of our set. So why are we using set? We could have just used first and last occurrence. It's because the fact that which occurrences are there will be useful later also when we have queries. Fine, that's why we're doing it like this. So L and R will be the leftmost point where our prime occurred. R will be the rightmost point where our prime occurred. And here we're simply marking these 2 points. So count L will be 1 and count R will be R. And why am I doing this? Because for every prime, if I mark, let's say the array was something like uh, 1, 2, 3, 2, 3, 2, 1, 3, right? So we're marking the first place for count L. For count L, we're marking the first place where each prime occurred. So 1 occurred, 1 is not a prime, so this will be 0. 2 occurred first time over here, and 3 occurred first time over here. So this is what our count L array looks like. Fine. And then we will do a prefix sums of this so that um, we recover that how many distinct values we're getting. All right. Similarly, we have a count R where we mark the last places where it occurred. And then simply what we do is we create prefix L suffix R. So this is our prefix and suffix array, which I explained. This is our prefix and suffix array, which I had explained. And we generate it by simply doing a prefix sum. If I is greater than 0, then we add prefix of I minus 1 and we add count L. And for suffix, we go from n minus 1 to 0 and we create the suffix sum at that point. And then what is T? T is our total or our answer. So total at a position will be prefix plus suffix. So this is from our second observation. So T of I equals the prefix at that position plus the suffix at that position. And that becomes our answer. So prefix of k minus 1 and suffix of k. So almost exactly this formula. Right. So now we have found for our initial array all the possible answers. So if we had to print the answer for the initial array itself, it would be the maximum value of T of I so far, or the maximum value of total so far. Okay. Now how to handle updates? How to handle updates? Right. So that is the big question. That is the main part of the question. So now that we know the structure of the problem, what happens in an update? So in a given update, at most one value is being affected, right? So at most one value is being affected. Now, if the affected value is not a prime, we don't really care. Okay. And if the affected value is a prime, then it matters to us. So again, let us say the array was something like this. And let us say this value of 3 is being affected. Okay. So let's say this value of 3 is becoming a 4. So this value of 3, which was a prime earlier, is becoming a 4. Well, in this case, our answer will not change since we know the answer only depends on first answer of 3 and last point of 3, right? We know that our answer only depends on first point of 3 and last point of 3. Answer will not change here. But what we will do if the 3 is being removed, we will remove it from our set of occurrences. So from our set of unordered map of occurrences, we'll find unordered map of 3 and remove it from that set. So this is just to keep track that there is no 3 any longer here. And then we can change the array and put the original value here. Okay. Now, so now let's say if the first value was being changed. Okay. So let's say this value of 3 was being changed to a 4. Then what do we do? Now we know that because of this 3, we had a prefix value of 111111 all the way here. Because all of these have a 3 in the prefix. So we can so basically yeah, so basically any k which starts ahead of this was getting a 1 increase to an answer because it had included 3, right? But the thing is now what happens? This will become the first value of 3. So if this becomes 4, if this becomes a 4, then this will become the first value of 3. And our prefix array should have looked like this with these values being 0. So basically these values have been changed to 0. The values between the old first value of 3 and the new first value of 3, in between all the values have been set to 0. And why have they been set to 0? They have been set to 0 because the value of the first value of 3 has shifted, right? So what does this mean? What does this mean in like terms of the answer? What it means if we took a split over here, then it would not include 3 in its prefix. It would not include 3 in the prefix. While as earlier it would have included 3 in the prefix because there was a 3 present here. So basically the answer for a split at this point has become -1. So the answer for a split over here and over here has been added by -1 and the remaining points have been unchanged. So that's what happens when we remove a prime. Okay. And what if we change the last prime? Well, a very similar thing happens, but it happens to the suffix array instead. A very similar thing happens, but it happens to the suffix array itself. And what happens is if we remove this last 3, then this becomes the new point of last 3, right? And then the suffix sum, instead of being like this, the suffix sum becomes like this. And then these values become 0 because there is no 3 in the suffix anymore from this point on. So basically we need to do a -1 on these 2 points. So this is how updates are functioning. And what if we were adding a new prime during an update? Okay. So what if we were adding a new prime during an update? So for example, there was some number 4, which is a composite number, but we converted it to a new prime. Let's say we converted it to a 3. So if there were already 3's in the array, and if it was a 3 somewhere in the middle, it would not affect the answer. But if it was, let's say, the starting value of 3, so there are 3's, but they're there later, and this was the starting value of 3, then what happens is basically this will add like a prefix. Yeah, this would add a prefix of this value of 3 to the sum, basically. So all the values of 3 from this point onwards, so all the values of prefix from this point of onwards would have a new prime to pick, basically. So if we had to split k over here, then this prefix now has a value of 3, right? So that's why we have to add 1 to every point afterward, or at least to the next 3. So basically what we can see is every time we add or remove a prime, if it is not the first or last prime, there is not much change. We can just delete or remove occurrence from our set. But if it is the first and last value of prime, then we need to update our prefix or suffix, or basically update our answer or total. So we can update our total of I, which is basically the prefix plus suffix, right? So L of I plus R of I, right? And we update this accordingly. And how do we update it? We need to take some range. So let's say if we got a new leftmost value, then this was the old leftmost value for some prime L dash. And for all of these values, we need to add +1, right? And the other form of update is, let's say we found some new, if the old leftmost value was here, but that value got deleted, and now the new leftmost value is this. So this whole range gets added with -1. Similarly for rightmost values. So these are the possible operations which are happening. So this is our, let's call this third observation. So we're changing the answer array. Each query changes our answer array. Each query affects our answer array, affects the array answer, affects array answer or total, depending on what you want to call it, by adding +1 or -1. So this is our observation 4, you could say. Observation 4. By adding +1 or -1 to some ranges LR. And sometimes an old prime is getting removed and it's getting converted to a new prime, right? So we might have to do like two operations. First to remove the old one, then to add the new one. So there will be some operations, but all operations are of this form. We're adding +1 or -1 to our answer array in some ranges. And answer to each query is the max of all values in the answer array. So it's max of answer of I for all given I. So what does this tell us? What does this tell us? We need a data structure. We need data structure which performs the following two queries, which is range sum. It performs a range sum. This is the first query which it performs. So for a given range, add some x or subtract some x. And the second query which it performs is find max of range. Find max of range. So we need a data structure which can handle both of these queries. Once we have reduced the problem to this part, that we simply need to, for each query add -1 or +1 between some range, depending on where the last and first point of each prime has been moved, then we know that we can simply make a data structure for our answer array, which can satisfy these two queries. And at this point, if you have studied segment tree, you know that we can have a data structure called segment tree, which performs exactly these queries. In fact, the whole reason for making segment tree is to solve questions like this. So we need a segment tree which can perform range sums and find max of range. Now, I'll not explain segment tree right now because if you don't know segment tree, this is a fairly advanced, I think, question of segment tree. So you should probably learn that first. It is there in the TLE Eliminators course. It is there on YouTube. It is there on CP algorithms. It's there almost everywhere. It's on Wikipedia. So definitely learn segment tree. I'm just going to tell you that there exists such a thing called segment tree. The way it works is it's like a tree and it maintains lazy operations. It maintains something called lazy operations, which perform these operations of range sum and find max, and they perform it in amortized n log n. So it can find you max of range in n log n. Sorry, it can find you max of range in log n, where n is the number of elements in the segment tree. It can perform range sum also in amortized log n, where n is the number of elements in the segment tree. So if you don't know segment tree, please watch it on YouTube or something. Um, to explain segment tree right now would take an extra half an hour, which we don't have. Also, if you don't know the implementation of segment tree because it's a complicated segment tree, look, you could always go to Geeks for Geeks and copy paste that segment tree template. Because I participated in ICPC and we had made a template for segment tree before, I just went to my ICPC notes and I copy pasted the segment tree template. We made a general segment tree template where we had all the possible operations and updates. So I just copy pasted the segment tree template directly. So, and I used it to find the answer. So once we have a structure which can perform these two queries, the remaining answer becomes very simple. Simply use observation 3 and find the correct places to update. So if it becomes if the prime's leftmost point becomes more or the prime's leftmost point becomes less, we can update in the segment tree accordingly. And you might need to write down, right? You might need to write down if the old value of the prime's leftmost point was L dash and the new value becomes L, then in this range L dash to L, you can figure out whether to add plus or minus one. Simply if the old prime value was R dash and the new position is R, so in this range R dash to R, you can figure out whether to add a plus or minus one. And once you have figured out these things, like that's very basic, I guess, you can simply use the segment tree to perform that operation. Once you perform that operation, you can find max of the entire tree and you can get your answer. Let us look at the code for this. So yeah, here I am just using my segment tree template. So don't worry too much about it. Sectree dual is the name of the template. And I just simply say that, okay, it's an integer or I'm building it on the array T. Okay. So I'm building it on the array T and the operation we're applying is for a given node, we add some value. So that is the operation which is being applied. And the update operation is max operation. So, sorry, the query operation is max operation and the update operation is addition. All right. So I made a segment tree in which the query is for max and the updates is for addition, which is what we wanted. So then um, after that, we need to know for each query which index was affected. What was the old value at that? What is the new value at that index? What was the old value at that index? Okay. So if it is a prime, if the old value is a prime, that means the old value has been changed, right? So we find out the occurrences. We find the first occurrence of L. We find the last occurrence of that prime. So if the old value was a prime, then we find the first and last occurrence. So old L and old R. We remove that occurrence from the set. So from our set in this unordered map, we have that set, right? So the set in our unordered map, we erase the occurrence of the thing because now we're removing this. And also, if the new value of L and the new value of old value of L don't match, then we need to update our segment tree by adding plus and minus one. So basically what I do here is directly till the old L point, I add a minus one, and then till the new L point, I add a plus one. So instead of having multiple cases like this, I can just do one case, like till old L, subtract minus one because this old L was removed. Till new L, add a plus one. And similarly, I can update the seg tree here as well. Then similarly, if the new value it was a prime, if the new value was a prime, then again I find occurrences of that prime. I find the first and last occurrence, and I respectively update my segment tree. So if this prime was appearing for the first time, that means it's an empty. That means that occurrence will be empty right now, right? So if the prime was appearing for the first time, then I need to do nothing but normally update my segment tree. Otherwise, if this prime was already there in our array, we find its old L value, old R value. We insert this element, find new L value, new R value. If the new L and old L have changed, if the new R and old R have changed, we update in our segment tree. Finally, we update in our array itself. So the indexed value of our numbers array becomes val. And then finally, we can push back our answer. So our answer will simply be the query of the whole range. So query of minimum from 1 to n minus 1 in our array. So in our answer array. So basically that's how you implement it. I'm sure like this question was slightly harder. So if you're familiar with segment trees, if you've done problems before, I think the idea is straightforward. If you are not, the recommend after this session, go through the code. The problem link, the code links will be added to the YouTube video description soon enough. So go through the code once. Um, this is just a segment tree template, so don't mind too much. If you don't know segment tree, please watch it on YouTube and learn about it. This is to just check if a number is prime. This is the basic part which I explained in the start. And here I'm defining a segment tree, and here for each query, I am updating in my segment tree, and then finally I'm returning the vector. So do go through the code afterwards if this is not understandable. Pratham Chermani, yeah, so I was able to solve only one problem. Yeah, so don't worry too much, okay? So sometimes you're only able to solve one problem in a contest, and it happens because sometimes the contest simply wasn't good, the questions weren't to your style. So I said, do not worry about, the results you're getting and focus on the process. Like if you like keep practicing and keep up solving, like right now you saw me solve these questions, right? You saw me just give an explanation. You saw me explain the code. Now, without looking at my code, without looking at this, you can try and implement it on your own. So if you don't get, let's say if you don't get, if in a contest you go, if there were a contest, there was A, B, C, D question, and you got only A, then you should definitely absolve B and you should try to absolve C. Okay. And if in a contest you got, let's say A and B, if you got A and B, then you should definitely absolve C, and try to absolve D or see the solution of D. All right. So that's how you should treat contests. And if you're having, let's say, um, like theoretical troubles, if you feel like you're missing a lot of theory, or if you need support, if you need doubt support with high-rated mentors, then definitely check out the TLE self-paced course. If you're already in the course, then definitely make doubts, and if you wherever you're getting stuck, ask help from mentors. And over time, with practice, with a few months of deliberate practice, you can solve more problems for sure. Okay, let us just analyze the time complexity of this question, and then we are done. So first, for every number, in nums, I'm checking if it's a prime or not, right? So what is the time complexity of that? That will be n root of a max. So a of I, sorry, nums of I goes to 10 to the power 5, right? So it'll be a root of nums max in the worst case to check if a number is prime or not. Okay, so that is this part. Then to build count L and count R, that is all big O of 1. Okay, yeah, because we're inserting in a set over here. This is an unordered map, so there is no overhead, ideally. But to insert in a set, again, it will be log n. So here we get a log n factor to insert into a set because a set is a red-black tree and each operation is log n. Then again, these are some n log n operations. This is O of n, this is O of n, this is O of n, this is O of n. This part was n log n. Then we're building a segment tree. Building a segment tree also takes n log n time. So since n root nums max log n is bigger than n log n, I'm not writing those complexities. This complexity overshadows those. Then for each query, so we have Q. What is the time complexity per query? Well, we have to check prime again. And based on the prime, we are doing operations in our set and we are doing operations in our segment tree. Operations in the set is also log n. Operations in the segment tree is also log n. So each query is multiplied with square root of nums max log n. So overall, our time complexity is something like this. And if you observe that for the given time complexity, this is just fitting. So N and Q have the same max, so I'll just consider it as one term itself. So I'll say roughly, and this is nums max goes to 10 power 5 and log of, so something like this, roughly number of operations. So in this approximate order of operations we get, obviously the constant term is a bit high here, so maybe 10 times this operations or five times this operations. But yeah, how much will this be? This will be, so yeah, it is roughly about 10 to the power 7-ish. Yeah, 10 power 7-ish. So it is on the limit again, so, but it's comfortable. Like we can do up to 10 power 8 operations. So yeah, it's definitely doable. And as you can see, we can definitely optimize this. So instead of a set, if you had used some other, maybe you could have used an unordered set, or actually unordered set is also a bigger, decent amount of overhead. So if you apply maybe some small optimizations here, you could speed up this code. Also, my segment tree is a very general template of segment tree, and it builds a lot of stuff which is not necessary also. So if you find a nicer template of segment tree, you can do it faster. Also, to check is a prime or not, we could pre-compute whether all the numbers from 1 to 10 to the power 5 are prime or not. So instead of each check taking square root of n, each check could have just taken constant time, one with some pre-computation. So then we can reduce the square root of this thing factor to O of 1. So that way we can improve the time complexity. But then this is still a simple to understand solution, I guess. That's why I don't do all those extra optimizations. But yeah, this is a valid solution. Okay, so we have come to the end of the stream. I think we have discussed all the problems. If there are any doubts, you can ask it now. Otherwise, we'll end the stream. Again, as a reminder, the TLE self-paced course is live right now. You can join it, and it has video lectures on all the topics, pretty much every topic which was done today: brute force, bit mask, PFS, segment tree. There are video lectures on all those topics in different levels of TLE. There is practice problems and dedicated hints for all the problems. There is a doubt support team, which includes me and other high rated mentors. So, yeah, thank you for attending the stream, everyone. And I hope you learned something. Bye bye.